Yeah, focusing on string field theory, which will be about applications of string field theory into DCF.
Right. So let me start with a conceptual recap of what we did in what we discussed in the first two lectures, and also give you some motivation on why it's beneficial to consider the implications of string field theory into DCFT. So one of the key points which we looked to during the last lecture was the action for a full interacting string field theory, which you can write down given that you start with, given that you have a knowledge of the consistent string background. So this is the action which is written in terms of a string field. So string field, that is something which we are discussing during the first lecture. That was a generic state, like a combination of states in the Hilbert space of the worksheet CFT and a particular ghost number. So the worksheet CFT was in turn a combination of a merger CFT and a BC ghost CFT. That's where the ghost number comes in. Then during the last lecture, we were also discussing this interacting bit, whereas the kinetic part, that is something where we ended with during the first lecture. So in particular, we were discussing the algebraic structure of these interaction vertices, and in particular, having expressed these interacting vertices in terms of these maps Ln, which we call string products, we were able to go through this chain of hypotheses and say that the requirement that these interactions are built in such a way so that the Feynman diagrams given by this action reproduce the optional amplitudes. The requirement that we get the full optional amplitude from the Feynman diagrams is equivalent to saying that these string products Ln, that they satisfy the axioms of infinity. So that we did for the closed string case. For the case of the classical open string field theory, that we remarked last time, that one would have to replace these L's by products which we call M, which were on a cyclic. So these L's for the closed string, remember they were built in such a way so that the vertices of the action and in turn the offshore closed string amplitudes were totally symmetric in the external X, right? Whereas for the open string, you're observing that the open string offshore amplitudes they have to preserve the ordering of the external X along the boundary of the disk, right? So the corresponding string products M for the open string, they were built in such a way that the corresponding vertices of the action were cyclic, to preserve the cyclic ordering of the open string insertions on the boundary of this. Right. So that was the action. Now the other key point which we were emphasizing at the end of the last lecture is that the solutions of the equations of motion derived by varying such an action should be thought of as corresponding to other consistent string backgrounds. So the idea is to define a worksheet CFT, given the worksheet CFT build this whole optional action, then the vary the action derived classical equation of motion, and then looking at the solutions of this classical equation of motion is equivalent to this going to other consistent strings. So that we were seeing quite explicitly at the end of the last lecture, where we were taking these classical solutions, we were expanding this offshore action around these classical solutions, and we were observing that the action which is satisfied by small fluctuations around the classical solution was another. We were getting another action whose vertices were obeying these algebraic constraints like L-infinity algebra. So in the case of a Go string, in the case of a Go string field here, we are also pointing out that these new consistent string backgrounds, which we obtain by solving the classical equations of motion string field here, they may or may not correspond to other Virchit CFDs, right? So consistent string backgrounds do not generally equal to Virchit CFDs, right? There are known examples of consistent string backgrounds which are not thought to be associated with Virchit CFDs, like NS5 brains, ADS5, CrossS5, run around flux or whatever, right? So the situation in open string field theory, on the other hand, is a little bit different. So in open string field theory, the idea is that that whatever happens, we are fixing the bulk, the CFD in the bulk of the Virchit, that is the CFD that is described in the Go string, right? So having fixed a bulk CFD, and then initially also some consistent boundary CFD, which is describing the open string sector, you can formulate the corresponding string field theory action for open strings. And then the solutions of that open string field theory action, solutions of equations of motion corresponding to that open string field theory action, they should correspond to other consistent open strings. But leaving the Go string background untouched. So, in other words, solutions of the equations of motion of open string field theory, they should correspond to other consistent D-brane systems or D-branes for the fixed Go string. So that's the situation in OpenSFD, and then then we can really rephrase the statement by saying that the solutions of equations of motion or OSFD, they correspond to other BCFDs, to other boundary conformal field theories for the given fixed CFD in the bulk of the Virchit. So we can kind of see that in the conventional Virchit approach to string theory, one really uses the 2D CFD as a tool to compute some observables related to strings, right? So we fix the CFD on the Virchit and compute some amplitudes, right? So now having said all of this, we can see that in the case of string field theory, we actually have a potential of going the other way around, right? So the idea would be precisely to look for new CFDs by solving the string field theory equations of motion. So this program seems to be especially viable in the case of open string field theory, right? As we were discussing during the first two lectures, in the case of open string field theory, in contrast to the Go string field theory, we have a complete knowledge of the action, that's the cubic written action. And actually, there is a very strong statement which has been proved in 2014 by Ada and Macaffery that starting from an open string field theory formulated on a fixed D-brane background, so fixing bulk CFD and some boundary conformally consistent boundary conditions, we can actually find any other consistent boundary conformal field theory for the given fixed bulk CFD by writing down a solution to equations of motion of string field theory. So that means that if we are powerful enough to classify all possible solutions of open string field theory, that should be as good as classifying all BCFDs for the given CFD.
So what is the definition of BCFD for the purpose of this statement?
So the definition of BCFD is a conformally consistent boundary condition for the given bulk Virchit CFD.
So the bootstrap definition.
Yeah, BCFD data. I mean, some data like boundary state coefficients, bulk boundary, OP coefficients, boundary frequent functions satisfying some Garde level and Sewing conditions.
So is it the case that in this case the bootstrap conditions kind of explicitly become the equations of motion for the open string field theory?
I guess in some very entangled way, but yeah, they should be equivalent.
This is what I want to ask basically. This last question. Yeah. Thanks.
Yeah, and yeah, I think it would be it would be an interesting project to see the connection. Yeah.
Can I ask another question? So before about the closed string, you made the remark that there could be solutions of the string field theory equation of motion which do not correspond to actual worksheet CFTs.
Yes.
Are there some maybe workable, more explicit examples of this phenomenon in the case of the open string, where you fix the closed string and you look for something that doesn't really look like a deep
so I think in open the only example which I can think of in OSFT which does not really correspond to BCFT is the tachyon vacuum. So the tachyon vacuum, that's a solution basically describing the D-brane on which you formulate the SFT disappearing into closed string radiation and remaining just with closed string background. Strictly speaking, I wouldn't call it a BCFT, right? It's a solution where you destroy the open strings, where you destroy the boundary condition. I mean, it's like maybe you can call it like a zero bounded state, but I'm not sure this is a good BCFT. But otherwise, I think the belief is, and no one really considered and constructed any counter examples yet, is that the solutions should really correspond to BCFTs, and there shouldn't be anything else. Yes.
We know one example of boundary conditions of two dimension, which is the FCCT and the ZZ branes in the case of Liouville theory. To what this corresponds to on the open string theory side, is it known? Or?
Yeah. So again, I mean, as in the case of any other CFT, what you have to do in order to actually formulate the action of the open string field theory, you have to choose a consistent boundary condition to start with, right? So let's say in the case of Liouville, you can choose a ZZT, right? And then the meaningful question to ask: can you find a classical solution of this open string field theory which would correspond to some ZZ, let's say? Okay. Yeah. But yeah, the problem with open string field theory, actually the problem with string field theory in general, is that it's not background independent. Or that is okay. That is not manifested background independent. Of course, it's believed to be background independent, right? But yeah, the fact is that you have to fix a boundary condition to start with. It's not like writing down an action for gravity like Einstein-Hilbert, right? Which is background independent, and then you can look at classical solutions, right? That should give you, all the consistent backgrounds for gravity. I mean, this lack of manifest background independence forces you to choose a boundary condition to start with. But then, in the case of OSFT, the claim is that it is fully background independent, although in a not manifest way. And that's starting with any consistent BCFT, you should be able to get to any other consistent BCFT by constructing classical solutions. Okay.
You may get to things which are not necessarily BCFTs also, like you said, tachyon vacuum. I guess I don't really.
Yeah.
In the case of a closed string, I don't quite know what you mean when you say that there are solutions which do not correspond to worksheet. A CFT is not the same thing as a string background, right? There you need to add the basically BC ghost and look at cohomology. So yes. The map between CFTs and string theories is not one-to-one. I guess there could be maybe different CFTs that do this procedure at the BC ghost and do cohomology, then you get the same thing. I guess it's a little confusing.
So you think that there could be two different matter CFTs, which upon adding the BC ghost system will produce the same spectrum, same amplitudes?
I guess what I want to ask is, how do you know that some solution of open string field theory is not actually a CFT? Because the data that you get is the data that you would get from a CFT after performing this gauging procedure, right?
Yes. Yes. Yeah. I guess that's that's a good question. Yeah, I guess what I just wanted to say that there may not be solutions to that there may be solutions to SFT which may not be CFTs, right? But the actual way of diagnosing whether this is the case in your particular solution which you give me, I mean that is of course a question by itself. Okay, so yeah, so that's the idea, and so yeah, you are saying that this idea of looking for new CFTs by solving SFT equations of motion, that it's especially should go through very well in the case of open string field theory. But even then, however, one has to remember that the equations of motion of string field theory are very hard to solve, and yeah, I cannot put enough underlines here. Although they may look kind of simple at this algebraic level, which I was writing down last time, and yeah, especially in the case of the cubical SFT, right? Remember, I mean, in the case of cubical SFT, I mean, all the higher interaction vertices they were just vanishing. So in the case of cubical SFT, that equation may look very simple. It looks like a Marrow-Cartan equation, right? But then you have to remember that the string field, that is an infinite linear combination of states in the Virchie CFT, right? So that has to be expounded as in an infinite basis with an infinite number of coefficients. So that simple equation actually turns into a system of infinite equations which are nonlinear for an infinite number of unknowns. So this is a hard thing to do, to solve such an equation. So a very fruitful approach, which was explored in recent years by many people, in particular by Maciej Kudla, is to solve these equations numerically. So this numerical approach is called the level truncation. And it is really what the name suggests. So you take this infinite linear combination of basis states with this infinite number of coefficients, and you just truncate it at some finite level. Or by level, I mean the combined level of the worksheet matter angle CFT. Right? So that will turn the system of equation into finite number of equations with finite number of unknowns. And then you can hope that whatever classes of solutions you find for these finite number of equations, they will actually converge as you increase the level. Right? So that's the idea, and I mean it actually works very well for minimal models, for free boson, for WZ, WCFT, and all these which you can look at. So that's one possible approach.
There is no such thing as some consistent truncation or low energy truncation or something that would be.
Yeah. So then there would be other approaches, right? Actually an approach which is very related to what I'm about to start now, and these are the marginal deformations, is to divide the Hilbert space of these states into two groups, one of which you call like massive states, and those you integrate out. By integrating them out, you're basically throwing away all the solutions which would be excited by these massive states. So that you may not be interested in. And you may say that what you are interested in are solutions which are built from the massless states, right? And those you leave in the game, right? So what you first do, instead of solving this equation of motion, you integrate out classically, you integrate out the massive states from this action. So you think an effective action for these massless states, right? So that is like your supergravity action or whatever, right? And then you solve the equations of motion for these massless states. So
Are you going to explain that, or?
Yeah. Okay.
I mean, how is it different than supergravity?
Yeah. I was not originally planning to talk about it, but I will comment it. So I will comment on it like in 10 or 15 minutes after I go through. Okay, so I was going to start talking about marginal deformations, and these marginal deformations actually are precisely a class of solutions which survive this procedure of integrating out the massive states, right? So the marginal deformations, they are present. They are generally present for any string backgrounds which is somewhat Ui, right? So if you have, let's say, some KLBL compactification with a non-trivial moduli space, or I mean, we don't have to be as complicated as that. We can just consider compactification with some torus or some couple of circles, right? So then we have the radii of the circles. So these are the moduli of the background. So in that case, you can consider marginal deformations of your background, which corresponds to you going to different points in this moduli space, right? And as we were already pointing out a couple of times before, these marginal deformations, they are excited by states in the version CFT, which should be considered lossless, right? So precisely, those should be the solutions which should remain visible after you integrate out the massive piece of freedom. So yeah, just to record some of these examples. Then, for instance, consider the meta CFT. Actually, sorry. I forgot that I already prepared marginal deformations. Sorry for that. So just to consider some of these examples. We could for instance consider the meta CFT to be just a free boson which is compactified on a circle with some radius r, right? Then of course, in order to have a consistent version background, we need to accompany this free boson CFT by something which has center charge 25, right? Because this is center charge 1. But that will basically not be interested in, and that factor, we call it CFT auxiliary, will just go on for a ride. So then the worksheet action for this free boson factor of the meta CFT, I mean that should be familiar. That goes as follows: where if the boson is to be compact, we are identifying it. We are identifying the values of this worksheet field X with that of X plus 2 pi. So here I chose a particular normalization. I mean, usually people choose a normalization where you identify X with X plus 2 pi r, where r is the radius of the compactification. But you can of course always rescale so that this r, the radius of the circle, then reappears at the level of the action. Whereas this boson field is identified as X plus 2 pi. So then, in order to change the radius of this compactification, either you can do it by hand, of course, you know the spectrum and the CFT, I mean explicitly, and any value of this radius. But you can also consider changing the radius by turning a particular interaction on the worksheet, and as you can actually read off from the action, you can expand this r in r plus delta r at the level of the action, and you can directly read off that changing the radius corresponds to adding the following interaction to the worksheet action. So if you add this interaction, which you can read off that it's marginal to the action, and you follow the usual rules of conformal perturbation theory, you will find that this precisely changes the radius at the level of the spectrum and the correlations and whatever. So another example would be exploring some finite part of the KLBL moduli space, starting from some special point where we actually know what a worksheet CFT is. So that could be a Gepner or free orbifold point, and many other. So now we would like to obtain these marginal deformations as classical solutions of string field theory, right? So that is we should always start with some consistent worksheet CFT. So we should pick a point in this moduli space of marginal deformations where I mean around which we formulate our string field theory action, and then given the action around that particular point of the moduli space, we should first find a solution to the string field theory equations of motion. So here I written the solution as phi star of lambda, where lambda is supposed to be some continuous parameter which will parameterize the solution. You know, I mean, we expect the marginal deformation to be a continuous family of solutions, which will take us to some finite distance in the moduli space. So lambda is just a label for this continuous parameter of the classical solution. And then given the classical solution, of course, I mean, just having the classical solution is not enough. I mean, there is no way of a priori saying to which point in the moduli space this solution corresponds to. So then we should go and try and extract from the solution some CFT or boundary conformal field theory data as a function of this lambda, and that should hopefully be able to tell us, I mean, at which point in the moduli space we go to, right? So in the case of, for instance, in the case of this deformation which increases or decreases the radius of the circle on which we compactify, right? This parameter lambda should somehow be connected to the change in the radius, right? But the precise map between lambda and delta r needs to be fixed by computing some observables and comparing the observables, right? So then, as we expect the solution to exist for continuous values of this parameter lambda, in particular for small values of the parameter lambda, we can actually hope to solve the equations of motion of string field theory perturbatively in this parameter. So for that, we can write the following ansatz for the classical solution phi star of lambda as a power series in this parameter lambda, and then we can try and solve the equations of motion of string field theory order by order in this parameter lambda, right? So the first thing to do would be to take this ansatz phi star of lambda for the solution and substitute it into the equation of motion of string field theory, right? So I can actually remind you what it was, right? So here, for the sake of definiteness, I chose to do the example of ghost string field theory. So in the case of ghost string field theory, when divided the action, remember that the equation of motion which we got last time is the following. Good, right? So now when you substitute this power series in lambda, you can read off and demand that the solution that this field configuration phi star of lambda solves the equation of motion. For all lambda, you can read off the coefficients in front of individual powers of lambda, and these are the conditions which you obtain. So then we have to go through these conditions order by order in lambda and ensure that they are solved. So this will be our first example of actually a solution of string field theory. So let's do that. So before we try to solve these conditions, it is useful to recall some facts which we already stumbled upon during the first two lectures. So you remember that the anticommutator of this BIST charge Q, V0 plus was equal to L0 plus. Or one more thing to remember is that V0 plus we are defining as just a positive linear function, V0 and V0 bar. V0 goes to 0 model B ghost on the word sheet, and L0 plus goes now goes to L0 plus L0. Okay. Then the other thing to recall is that there was a particular choice of gauge, which we call a Siegel gauge, and in particular that was the gauge which is imposing the V0 plus on the string field 0. That was the Siegel gauge. And in this Siegel gauge, we remember that we had this property that one can always choose a representative of the BRST cohomology, which is whose eigenvalue with respect to L0 plus was 0. So that is, there was a choice of a representative of the BRST cohomology, which was in the kernel of L0. So for that, it's useful to define projector. We define this operator P0 plot, which is going to be this projector on the states in the kernel of elements. So the image of this projector, the image of P0 plus, will be precisely equal to kernel. Well, so it's all states which have the vanishing total worksheet dimension, the total worksheet scaling dimension. So now, given this, given these facts, let me go order by order and try and solve this. So these conditions for the marginal deformation to exist. So we see that at order lambda to the 1, we are just obtaining the statement that that this leading part of the solution should be BRST ghost. If it was BRST exact, we could actually then argue that the solution which we're obtaining is pure gauge. Is a pure gauge transformation of the string theory equation of motion. So we can actually say a little bit stronger statement that at order lambda to the 1 we are obtaining the condition that this leading contribution to the solution is in the BRST cohomology, right? So in particular, if you are fixing the Siegel gauge, you can always we can generally write this phi 1 part of the solution as follows. C1, C1 bar are the C ghosts, and this operator V is an operator in the meta CFT which have left and right wing dimensions 1 and 1. So this is dimension 1, 1 meta primary. So I said that one can always generally write down phi 1 as that, but I should also mention that in a particular case of closed string field theory, there is yet another state which satisfies this condition that is in the cohomology, and that we call the Gauss dilaton. So let me write down the expression for the Gauss dilaton. Yeah. So that I will actually not consider from now on, but it's nevertheless interesting to point it out. So one could also build a marginal deformation solution starting from this state, from this Gauss dilaton, and the interpretation of that solution is that it actually doesn't correspond to a marginal deformation of the matter of CFT, but it corresponds to deformation which renormalizes, which changes the value of G string. Right. So one could consider the marginal deformation starting from this state, from this Gauss dilaton, and then compute some observables like the spectrum. One would find that the spectrum doesn't change, but one would find that the overall coefficients in front of amplitudes actually they do change, and they change with precisely the correct power which would correspond to renormalize the G string. So that's this Gauss dilaton, which from now on I will just forget about, and I will focus on marginal deformations which are induced by the states of that type, which are C1, C1 bar, and then some operator of dimensions 1, 1 in the meta CFT, and that is precisely the operator which corresponds to the marginal deformation inside of the meta CFT. So this is the So this is the leading part of the classical solution. And as we were discussing, since I'm choosing the solution to be in cyclic gauge, the generic feature is that phi1 is total where G dimension 0,0. That is, it lies in this kernel of plots. So that you can see immediately, right? Because here you have dimension 1 in the left, 1 in the right, whereas the C ghost nodes, they have dimension -1 in the left, -1 in the right. So in total you get 0,0. Okay. So now we should take this phi1 and feed it in this equation of motion which arises at second order in lambda, and try and solve this equation of motion. And that will be done in a number of steps. So let me start with step 2a. So what we first do is that we decompose this string field phi2 for which we are trying to solve into parts. Using the projector P0 plus which are defined. The part which projects inside the kernel of L0 plus I will call it a phi2, and the part which projects outside of the kernel of L0 plus I will call R2, and also this kind of conjugate projector 1 minus P plus I will call P plus 1. So that is step 2a. Yes.
Can you just remind us what is the a priori vector space in which phi the full phi lives? So it's you take the full meta CFT times the full BC ghost.
Exactly.
And that's it, or are there any restrictions?
In the case of ghost string, there is the restriction that the states are level matched, so they are killed by L0 minus and also by B0 minus, right? And also, if you are trying to find a classical solution of the SFT, right? So this that should be the same string field phi which enters the action, and that is also restricted to that particular ghost number, right? So in particular, in the case of ghost string, this is ghost number 2, as you can see. Okay. So that was easy, but now let's try and exploit this decomposition into little phi and R. We can also act with this projector on the equation of motion, and we can use the fact that since the projector projects on the kernel of L0 plus and L0 plus commutes with the BRST charge Q, the projector itself also commutes with the BRST charge Q. So we can actually act with P0 bar and P0 on the equation of motion and obtain these two equations. So first acting with P0 bar, then on the other hand, when we act with P0, again, the projector just goes through this Q and it acts on the string field here, so we get Q, right? But then these projectors, neither P0, nor P0 bar, they generally do not commute with these string products, so they just act on them from the outside. Okay. And here I have replaced this capital phi1 with lowercase phi1, which corresponds to the part of phi inside the kernel of L0 plus, because as we were discussing, at the level of this phi1, that was purely inside the kernel of L0. There was no component R1 which was outside. So just replace capital phi 1 with lowercase phi. Okay. So now comes another step. That is, we will try and first solve for this capital R2. That turns out to be actually easy. So I will just write down the solution, and then I will check that this that solution is indeed a solution. So solving for R2, find that it can be written as minus 1/2 V0 plus over L0 plus. Now, this in general would have been ill-defined, right? Because when I active this L0 plus on states which are in the kernel of L0, I would just get an infinity, right? So I need to protect this 1/L0 plus projector P0 plus bar L2. So now, of course, we have to check that this indeed solves that equation here. So let me quickly take you through the calculation. It's a quick exercise. So what we do, we take this R2 and we act on it with Q, right? And we will hope that we will get the other side of the equation with a minus. Okay. So first of all, what we do, yeah, I should say that that here this fraction is well defined, right? Because L0 and B0 they commute. So I could have written either 1/L0 plus times B0 or the other way around. Doesn't really matter. So I can just write this as B0. So so then when I activate this Q, it passes through this L0 plus, right? Because Q commutes with L0 plus, so you said. Then this Q will hit this B0 plus, and then I just copy the rest. Now I cannot just pass this Q through this B0 plus, right? Because they do not anti-commute. So I have to anti-commute it past, but in the process, I will obtain Q anti-commutator B0 plus, and then of course minus B0 plus Q. Well, that is precisely L0 plus, right? So then when I substitute, I get minus 1/2, 1/L0 plus, and L0 plus minus B0 Q. So then let's see what happens. We have obtained these two terms. So when you look at the first term, that is actually giving us precisely what we need, right? Because this L0 plus will precisely cancel this 1/L0 plus. And we are obtaining precisely this term with a minus, as we should, right? So that's good. But what is going on here? So here we have this Q, which is now acting on this B0 bar L2 phi 1 phi 1. So Q commutes with P bar. So that we can pass through, that's okay. So now we have Q hitting L2. So then you need to remember one of these relations which we are obtaining from this L infinity algebra of these vertices L. And the particular relation which we need to use here is that Q acts as a derivation of this product L2, right? So up to minus sign, Q can be passed inside this L2 and act on the insertions of L2, right? But then we need to go one step back and remember that phi 1 was defined to be killed by Q. Okay. Actually, that term vanishes. Okay. So what we end up with is precisely what we needed to end up with. So we have managed to solve for for part of this string field capital phi 2, namely for this part which we were defining to lie outside of the kernel well not. So now, as a final step, at this particular order in lambda, we need to worry about this remaining equation function. So we need to require P naught plus acting on L2 phi 1 phi 1 should be BRST equivalent to 0. So why I'm saying that, you can see that this equation can be written in the form that P0 L2 phi 1 phi 1 is equal to something BRST exact. Okay, so this is why I have written this still down. So then one has to ask what happens actually when we take this state phi 1 compute this L2 projected on the kernel of L plus, and we find that on the right hand side we are getting an element which is non-zero in the cohomology. So that can of course happen, and the interpretation then is that the marginal deformation which we're trying to construct is getting obstructed at this particular level in perturbation theory. So that, in other words, that is saying that the phi 1, the direction along the margin, that would be direction around the margin of manifold, which we're parameterizing by the state phi 1, is actually not exactly flat, and it's getting some potential. Okay, so then of course it is not automatic that when we write down a state which is inside of kernel of L0 and which is in the cohomology and which indeed solves the equation of motion at this order W1, it is not automatic that it will solve the equation of motion at higher orders, right? It's like saying, okay, we could have a field which is massless, which does not have a mass term in the action, right? But it still can have some higher order potential, right? Like for instance, the massless phi to the 4th, right? In the case of massless phi to the 4, I mean, the direction would be naively marginal if you just look at the mass term, but since there is the phi to the 4 potential, the direction is no longer marginal at higher order. Right? So this is precisely the phenomenon here, except here when we find an obstruction at order lambda squared, you can actually think of it as having cubic potential. So that rather than phi to the 4, that would correspond to phi to the 3. So so this is precisely where I think I can comment about what Mariana was asking. So there would be an alternative way of organizing this computation. So instead of going order by order like that, one could actually from the start divide the string field capital Phi without a priori writing this perturbative expansion in lambda. One could divide this string field capital Phi into a component which is inside the kernel of L0, so that would be like little phi, and component which is outside of the kernel of L0, that would be like capital R, right? But somehow, containing all orders in lambda. And then one could consider actually first solving the classical equation of motion just for this R, and leaving this little phi in the game, right? So that could be done. Or one could just solve these order by order. One could just solve these bar equations of motion, right? Leaving these p equations of motions unsolved, and that would actually yield the string field capital R as a functional of this string field lowercase phi, right? And one could then take this, one could construct the string field capital Phi as a functional of this unsolved string field lowercase phi, defined as phi plus r phi, right? And substitute this back into the action. So that of course will yield an effective action for the string field lowercase phi, which is defined to lie inside of the kernel of L0. And actually, that is algebraic. That is a very neat procedure. It is related to something which in mathematics it's called homotopy transfer, and so one can use theorems like homological perturbation lemma to actually derive the algebraic properties of the vertices of this effective action. And one can actually prove that that the vertices of the effective action again satisfy the axioms of infinity algebra. So this is this is as Marian was asking. This is how we would obtain, let's say, a low energy effective action like supergravity from the full string field theory. Well, we divide the string field into whatever we need to leave in the game, like the supergravity fields, right? And then all the massive excitations. Those we would integrate out, and following this procedure of integrating all these massive fields, we would obtain the low energy effective action. And then of course, we could look at the vertices of the low energy effective action. So the vertices of the low energy effective action, they should be interpreted as giving us potential for these these fields for these fields which are contained in the string field over case phi. Right. So for instance, the cubic vertex of such an action for the lowercase phi would precisely be given by phi p naught L2. So if this cubic potential is not zero, that is as good as saying that this guy here is not zero, and that precisely corresponds to this abstraction which we're finding. This order of the square. So this is roughly speaking how we can view these abstractions to finding the marginal deformation as arising from non-zero potential of an effective function.
That condition before looks a bit more general. Sorry.
Well,
how do we know that phi2 would be proportional to? No, sorry. I guess the point is that if you look at the second, so on the top blackboard, right, there is the second term on the bottom.
Yes.
That is, there's an obstruction if that term is not Q exact.
Yes.
So how do you know that the non-Q exactness is proportional to phi1 itself? Is that? I mean, isn't that what you're assuming down in the cubic?
Well, so how okay, so how do you in practice decide that this one is non-zero? So you decided by testing this term by let's say by computing, you know, the 2-point function, the BPZ2 overlap against some states, right? So here this lowercase phi here, I mean that is a combination of all states inside kernel L naught, right? Not just so this is like testing it against all states. So I guess that there are like
it's enough to test it against phi1 itself, right? We picked the directions.
Yes.
And then the operators, those being exactly marginal, if and only if the 3-point function phi1 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 is non-zero.
Oh, if there is some other light operator,
right.
there could be a potential, right? Yeah. Yeah. So I hope that this makes it a little bit more clear.
Let's go to question.
Yes, sure.
So because from the get-go you're working in the level matched subsector, right?
Mm-hmm.
Does it mean that you're throwing away all the information about spinning primaries in the original matter CFT? Those for which L0 minus L0 bar eigenvalue is non-zero.
I'm throwing away information about spinning primaries in the total worksheet matter plus go CFT, right? But still, I suppose I have all the information about spinning primaries in the meta CFT because I can compensate the spin in the meta CFT by negative spin in BC2C.
Thanks.
Yeah. So you see that we have built provided that there is no obstruction which we're discussing, we have built a classical solution corresponding to marginal deformation up to second order. So let me just summarize by putting everything altogether and writing this solution down. We'll add linear order in lambda, we adjust this by 1. And then for quadratic order in lambda, we were dividing the solution into 2 parts. First, we solved for this for these so as to speak massive components outside of the kernel node. And then we had this this phi2, which indicates that this P0 L25151 is not precisely 0, but still it is 0 in the Cohomology, saying that there is some state phi2 such that Q on phi2 can compensate this P0 L2. We have to add this phi2 to the solution. Okay. And then, of course, we can continue this procedure perturbatively order by order in one way. So then, straightforwardly, compute what the solution is of cubic order, etc., etc. So now, of course, okay, this is now a solution to the string field theory equation, right? But again, I mean, if let's say if this phi1 was to be this del x bar deformation or operator in the free boson, which is supposed to change the radius, at the level of the solution, it is far from obvious. Let's say what the relation between lambda and the change of the radius is, right? So we have to compute some observables. So focusing again first on the case of the closed string field theory, we could hope that we could get something from the on-shell action. Well, actually, this is okay. This is not just a problem of closed string field theory, but in general, you can see that the on-shell action for the marginal deformation is just 0. So why is this the case? So you can try taking a solution for marginal deformation and substituting into the action, right? So the first thing which you can say that when you set lambda to 0, the solution is just 0. So the action, since it is, since it doesn't contain any constant terms, the action will be also 0, right? So at lambda equals 0, you get a 0. So then you can try and differentiating this thing with respect to lambda. And using the chain rule, you can write that this is equal to the variation or the function, the derivative of the answer with respect to the string field, evaluated and a classical solution, times the derivative of the string field with respect to lambda, right? But then, if phi star is a classical solution, this one is just 0, okay, by definition. So not only the value of s at lambda equals 0 over 0, but also its derivative everywhere is 0. So that means that the action needs to be 0 everywhere. So that is not good actually. On-shell action doesn't provide us with any observable. So, but even if it was providing us with some observable, in the case of closed string field theory, as we were discussing last time, the interpretation of what the on-shell action should actually physically correspond to is not entirely clear. That situation will improve in the case of open string field theory, as we'll discuss later. So we'll have to look at some other observables. So in particular, one class of observables which would be nice to extract from this classical solution would be the scaling dimensions of the operators corresponding to the new CFT obtained from this solution, right? So a scaling dimension in the string language, I could say also the spectrum of masses of the string states, right? So, so, I guess there are various strategies of how one could obtain the information about the scaling dimensions of the new CFT, which we're obtaining as a classical solution of string field theory. So let me present one particular strategy, which I think was originally developed by Ashok-san. And that is based on the following idea. So we take the measure CFT, and we decompose it in several factors. So first of all, there will be the factor which I will denote as CFTC, where C is constant to charge. And that will be the CFT of our interest, where actually the marginal deformation is taking place. So that in particular is the CFT to which this operator V, H equal 1, bar equal 1 belongs. So that is the operator V, which we're using to start the marginal deformation, which we're using to define this operator phi 1. So that there will be the auxiliary sector, but in the auxiliary sector, we will identify one factor we will call CFTY, and which in general we will take to be a time-like boson. And then, so as to compensate the central charge, we will choose some arbitrary auxiliary factor, which is central charge 25 minus C, which again will not play any role in what we are about to discuss. So just for the sake of simplicity and definiteness, we will assume that this factor CFTC, in which we are performing the marginal deformation, is going to be compact, unitary, and yeah, have these nice properties. So then, in this factor CFTC, as we are performing the marginal deformations, the dimensions of states should change, right? So we should somehow be able to extract the change of the scaling dimensions of the states in the CFTC as a function of this parameter lambda of the classical solution. So that is what we are about to do. So in particular, let me choose a primary of some generic dimension h, h bar in this factor CFTC. So I said generic dimension, but again, for the sake of simplicity, exactly as Daniel was asking, so that I do not have to compensate the level matching, let me choose h to be equal to h bar. Well, I mean, this is strictly speaking not necessary for the method to work. I'm just choosing it for the sake of simplicity of the discussion. So then, the scaling dimension delta, which is just h plus h bar, can be written as x2h. So this operator u h, h bar, that is an operator in the CFTC around which we are formulating the initial background for the SFT. So, so this is to be thought of as sitting at lambda equals 0. So then using this operator u h, h bar, and also exploiting the fact that we are adding this factor CFTY over time like free boson, we can actually write down an element of the cohomology at lambda equal 0. You can see that as long as we fix this k, the momentum of this time-like free boson, we can always make this operator to be dimension 0. So in particular, we need to fix that -2. So this is -1 for the C ghosts, plus half of k squared, which is the dimension of this plane wave for the free boson Y, plus the scaling dimension delta of this operator U is equal to 0. So now, before we make a break, let me just outline the strategy of what we are about to do. So now the question is, can we actually construct an element of the cohomology around this classical solution phi star lambda, right? Which would correspond to the deformation of the state of the U, right? So as we were explaining at the end of the last lecture, one could construct an action around this classical solution by expanding in small fluctuations, and that procedure gives a shifted BRST charge, which is the kinetic operator, around this shifted background, right? And then we can ask, can we construct a deformation of the state, which was at lambda equal to 0, so that it remains to be in the cohomology of the shifted BRST operator, right? So that's the first thing to do, and then the second thing to do, from this deformed state of the cohomology, we'll somehow try and read off the scaling dimensions of this operator U, which would correspond to the shifted background. So let's make a break here.
I keep the YouTube active, so you know.
You said the action, the alpha action is 0 for anyone at this time,
Yes.
but your
So-
argument is not enough, right? You're just saying that at lambda equals 0 and the first order derivative is 0, but how about higher order derivatives? I think from the expression, it's not obvious that all derivatives is 0.
Oh, this is true at any lambda, right? I mean,
Suppose I have just a S equals lambda squared, then the first two orders are 0.
but then you can then you can repeat this argument that at any finite lambda. I mean, at any finite lambda, this is a solution. So phi star lambda is a solution to the classical equation of motion at any lambda, right?
I see, I see.
So it's okay. So the argument is okay. Oh, it is important to say that lambda equals 0 is 0, right? But then this argument proves that this is actually a constant. So this argument proves that as phi star lambda is equal to a constant, doesn't depend on lambda. So in particular, I can choose any value of lambda, like lambda equals 0, to fix this constant.
Yeah, I can ask. The answer may be long. In which sense is the bug CFT fixed if you're deforming the boundaries? Like, how do you know? How do you know? Like, if you fix some BCFT, right? And then now you look for solutions of the open string field equation of motions, and you're going to find something.
Yes.
And like, how do you know that that something is a real boundary point for your original CFT? Like, some check that verifies this, or for example, the bug spectrum, say, the boundary state.
Well, you're just solving the open string field theory equation of motion, right? So
Yeah.
the ghost string field doesn't enter in any way.
Yeah, I understand, but I guess. Is there some check, an inconsistency check of this table?
I guess you can you can just write down the full open ghost string field theory, right? And then the open string field theory, the classical sector of open string field theory, will be just a subsector of this full open ghost, right? So then you can write down a classical solution to this open string field theory, expand around it, and you see that the ghost sector just didn't change, right? So that should be the same ghost string field theory in the bulk. Now the statement that the solution which we wrote down corresponds to another BCFT, another consistent BCFT, that I think is more at a conjectural level. That would be. You would have to prove that this satisfies the strap axioms for the open. That we didn't do, right? So,
No, if I understand right, like the state of the subject now is that it allows you to search for kind of arbitrary far BCFTs from a given BCFT, but
yeah,
but you can't do that for CFTs, right? Because the action is gonna know like perturbativity to
yeah,
first few orders.
yes.
Are you ready?
Yeah.
I'm starting the recording again. Okay, so as I was advertising before the break, we will now, given this element of the cohomology at lambda equals 0, we will try and first construct an element of the cohomology for the BRST charge. The action expanded around the classical solution. So before I do that, let me recall what that BRST charge was. So taking the classical solution, expanding its most fluctuations, substituting into the original SFT action, I can derive a new SFT action around the classical solution, and from that I can read off the BRST charge corresponding to the shifted background. So let me call that Q lambda, and let me recall how that Q lambda acts on states. So at reading order in lambda, it just acts as a Q phi, right? Then we were observing that we're getting some corrections to it. Lambda, phi, and then some other terms involving higher order string products, L3, L4, etc. Right? But as you can see, all of these guys, they will contain at least one insertion of the classical solution. And the classical solution for marginal deformation starts at order lambda to the 1, right? So all these guys can be thought of as giving you some higher order corrections to just acting with Q. Okay, so that is the shifted BRST charge. And so you can indeed verify that this is a good BRST charge in the sense that it squares to 0, but as a consequence of Q squaring to 0 and L2, L3, etc. satisfying the L infinity relations. And also as a consequence of phi star being a classical solution, you can prove that this operator little q lambda is indeed nilpotent. So then let us try and solve for deformation of this U, which would correspond to an element of the cohomology of this little q lambda. So the strategy we as follows. We will again do this perturbatively, but the perturbative scheme will be a little bit different than the one which we are using to find a classical solution. Instead of expanding order by order in lambda, we will actually try and solve for successive approximations. And the reason is as follows. So we will see that since the CFT which we're interested in here is compact and unitary, actually we will find that a different element of the cohomology will be a complicated state, which will, however, always start with the C1 bar, UH bar. We are not allowed to deform the state here, right? Because H and H bar, since the CFT is compact, I mean, these are just discrete values, right? So what on the other hand will get deformed will be the value of this momentum here, right? So, but at the same time, if you are trying to find a solution which will be expanded in powers of lambda, and knowing that we are getting deformations of k here, you would actually find that the coefficients in front of powers of lambda would be some logs of would be some derivative of this exponential, which would be in general not very nice states in the CFT. Right. So a strategy which turns out to work much better is to instead try and find successive approximations to this different cohomology. So let me define what I mean by these successive approximations. So we'll be looking for elements in the cohomology through U lambda with bracket n, such that at lambda equal to 0, these will all be just the original undeformed state U. That state over there. Okay. But at the generic lambda non equal to 0, when we active Q lambda, we will be getting 0 up to terms which are of the order lambda n plus 1. So this condition is basically expressing what I was saying, namely that the state u and lambda can be thought of as being a state representing the different cohomology, which is exact up to corrections of order lambda n to the plus 1. Okay, so that's the strategy. And the ansatz for these states u lambda n which we'll be using will be as follows. So the idea is to divide the expected solution for the C lambda n into two parts. One part, which should be thought of as lying in almost the kernel of L0, right? So it would have been exactly in the kernel of L0 if we were setting lambda to 0, and the scale lambda n would be exactly the scale which we're defining by this constraint there, right? But as we will start, moving in the moduli space, increasing the value of lambda, we should expect that in order to compensate, in order to compensate for these additional factors appearing in the equation for the shifted BRC charge, we should be getting that this momentum k will change slightly, right? And that in turn will make this state be no longer exactly in the kernel of L0, but for small deformations, it will be still almost in the kernel of L0. So this is almost in the kernel of oops. And then there will be this other part, which on the other hand, we will take to be far from the kernel of L0. Again, we will define some projector, let me call it for P lambda, and here some projector for P lambda bar, which we will use to decompose the solution for the different elements in the cohomology into two forms. And before I go and substitute into the equation of motion and solve for these two guys, let me now outline what the idea is then for reading of the dimensions of in the different CFT, right? So the idea is that the solution, the classical solution phi star, which we are turning on, since it is induced just by the state in the direction of the CFTC, which we're interested in, right? The idea is that the CFT of the free boson then just remains undeformed. So all the deformation happens just in the CFTC, right? So that means that whatever momentum gets turned on here, that is supposed to be turned on in precisely such a way so as to compensate for the change of the dimension in the CFTC, right? So the idea is then that
I'm a little lost because U is fixed, right? UH bar doesn't change.
UH bar is the state in the CFT at lambda equals 0.
That's right. And L0 plus also doesn't change as an operator.
As an operator, yes.
So if that doesn't change, so if that first part is in the kernel of L0 plus, then K also shouldn't change as a function, right? K is fixed by the dimension of UH bar.
Oh, but I said it's almost in the kernel. That's precisely the.
So it's up to order lambda.
Up to order lambda, and that should precisely reflect the real change in the dimension of this H, right?
So even as we increase the order of the approximation, as we increase n,
yes,
that doesn't mean that this thing gets closer and closer to the kernel of L0. It's still of order lambda.
It would get to the kernel of the shifted L0, of the L0 around the new background, right? But Yeah, here what I mean by kernel.
Yeah, that's exactly what I was.
Yeah. Yeah. So just to reiterate, the change in the momentum which we'll observe here should precisely reflect the change in the scaling dimension of the operator of the CFDC, right? Because you know that since we are constructing an element in the cohomology of the right, with respect to the kernel of the shifted element, we should be getting elements which are inside, right? So then the idea is that by measuring the scale lambda, we should be able to get the corresponding deformed scaling dimension delta lambda. I just keep it completing it as 2 minus lambda squared. Okay. Or this should be considered as the on-shell condition with respect to the shifted background. Right? So now let's try to do this order by order in lambda again, or order by order in the successive approximation. So to the order of accuracy lambda to the naught, we already done, right? So to this order of accuracy, U naught should be precisely identified with this little u, right? So now let's look at the order of accuracy lambda to the 1. So at this order, this equation of motion for u, or I shouldn't call it an equation of motion, it's an equation of motion for the shifted cohomology. This curly u lambda bracket 1 should satisfy this equation. So now we should go and solve it, right? So again, the strategy would be very, very similar to what we did with the marginal deformations. We act on this equation with this projected curly p and also curly p bar. So that will, since the projector, again, since the projector is kind of measured with respect to L naught, it will commute with Q, and we can split this equation into 2 equations. One equation will be for this capital R, and the other equation will be for this component, which since sits inside the kernel of L naught. So let's just write it down. Or almost in the kernel of L naught. So conditional can actually call this state here, little u lambda n, right? In analogy with this little u over there. So of course, we can notice that this state u lambda 0, again, this is just little u as the element of the cohomology which we're starting with at lambda equals 0. So now the solution for this capital R lambda, again, that's easy. That since basically the moral is that since we are projecting outside of the kernel of L naught, we can very safely invert this Q by the C2 propagator, and we can write that solution for this component R lambda 1 of the different cohomology is minus lambda B naught plus plus curly P bar L to 5 views. So using a very similar computation which we did explicitly for the actual solution for the margin deformation. You can verify that this is a solution to this first equation here. And then we have to go and use the second equation to try and solve for this u lambda 1, right? So since this u lambda 1 is written using this particular ansatz, using the known state in the CFTC which we started with, the only free parameter in this u lambda 1 which we have to fix is this momentum k. So solving this equation for u lambda 1 is as good as solving it for this k lambda 1. Okay. So that is then very straightforward. Once you notice this. So what we can do, we can just first of all compute this first term in the equation. We can act with q on u lambda 1. So what happens when we act with q on u lambda 1? So since we know that it is of this form, we know that in this particular case, when the solution is written in a CWH like that, acting with q is the same as acting with C0 plus R0 plus. That is something which we have noticed, I think, in the first lecture. C0 plus, remember, was just half of C0 plus C0 bar. So we'll have C0 plus R0 plus acting on u lambda 1, where R0 plus is just measuring the total scaling dimension of the state u lambda 1. And that we know what it is, of course. Given this form of u lambda 1, we can just read off that the action of L0 plus will give us -2, remember the see ghosts, then plus delta, plus half of k lambda 1 squared times u lambda 1. Okay. And by this equation here, we know that the result of computing q on a u lambda 1 needs to be equal to the result of computing minus lambda projector curl p on L2 phi1 p. Okay. So you see that indeed now the momentum here needs to get deformed a little bit, right? Because this in general will be non-zero, right? So in order to compensate for this being non-zero, I have to change this momentum k to be a little bit different than the momentum k which we are starting with, right? And yeah, so now you see that we can actually test this equation, take an overlap of this equation against some suitable state to actually compute this k lambda 1, right? Because then we already know what phi1 is and we know what u is, right? So that is precisely the way how we get this k lambda 1, and then in turn also the deformed scaling dimension. So the best way to proceed here is to just take this equation, this right hand side and this left hand side here, right? And compute an overlap of that equation with u. So if we do that, let me outline what happens. So first of all, one thing to notice is that we can replace this u lambda 1 with just u, right? Because since we know that this k will be equal to, so since this k lambda 1 will be equal to the original k up to order lambda corrections, we know that this bracket needs to be definitely order lambda, right? Because if lambda was equal to 0, this bracket needs to be 0. Right? So this is of order lambda. So since this is already of order lambda, and we are working at order, we are working at the accuracy of order lambda to the 1, we can replace this u lambda with u lambda 1 with u lambda 0, which is just u, right? So that's one thing to notice. And the other thing to notice is precisely that that this bracket here, this order lambda state, is nothing but delta minus delta lambda, right? Delta lambda to the particular order of accuracy, which is order lambda 3. So that you can very, very quickly derive by recalling how we define this delta lambda, this different scaling dimension. So delta lambda 1 would be 2 minus half of k lambda 1 squared, right? So substituting for k lambda 1 squared, you just very quickly notice that this bracket is just the difference of the original scaling dimension and the different scaling dimension to the first order of accuracy, right? So the leading order of accuracy. So then you can see that if the state U is suitably normalized, in particular if the state capital U H bar in the CFT in the CFT C of interest is suitably normalized, so that the two-point function is equal to 1, we can just compute this BPZ inner product of both sides of the equation against U, right? So then this U here will just disappear. It will be, I mean, we will get a factor of 1 from there when it's suitably normalized, times this bracket, right? And then on the right-hand side, you will get BPZ inner product of U against L2 phi 1, 1. So let me just write out the final result.
If your original answer was consistent, then this equation should be valid as a vector equation, not just when you project against a particular vector. So
of course.
it should. I guess I'm asking, why is it not manifest that the right-hand side is proportional to the same vector as the left-hand side? Why do you have to do this overlap?
I just want to. Okay, in principle, I don't have to. I just wanted to write down a formula for the different conformal dimension, right? And then show it that it is equivalent to the CPT result. So, but in principle, you don't have to, right? I mean, it's kind of obvious that it has to be proportional to U, right? Because U contains some momentum. I mean, in this direction of the free boson. So since this momentum needs to be conserved, it needs to be proportional to the same state from the model. So then, taking this overlap, we can compute that the different scaling dimension is equal to 2. So then we can also take this result and we can actually write it in a little bit more recognizable form. In particular, we can just try and strip away all the SFT data, and we can just write a statement at the level of pure 2D CFT, in particular at the level of the CFTC, which we're interested in. Right. So that is very easy to do. Actually, we can note that all the states which enter into this kind of SFT overlap here, that they are in the kernel of L0, they are massless. U is massless, that's the state in the cohomology which we're starting with, and phi 1 is the leading contribution to the marginal deformation, right? So that is like computing a frequent amplitude, which is actually on shell, right? All the states entering here are on shell. So actually the result of computing this term does not depend on the choice of local coordinates of the string field here, because these are dimension 0,0 states. So whatever local coordinates I choose, I mean, yeah, the corresponding conformal transformations, they will just drop from the computation. So this can actually be translated just to computing a pure 3-point function, which if everything is suitably normalized, gives us delta lambda 1 is equal to delta plus 2 lambda CUV. CUV is the 3-point structure constant of this corresponding to 2 insertions of this operator U, to 1 insertion of this operator V, which triggers the marginal deformation. And yeah, that is something which you can compare with the usual CPT conformal perturbation theory calculation, and it agrees. So then that was order lambda to the 1. At order lambda to the 2, we would just repeat. And you will get more complicated equations to solve. I had this example where I wanted to show you how this gets implemented in the case of the free boson, but in view of time, let me probably skip that. And let me just do a couple of remarks. So the first remark to do, actually, yeah, maybe it might have been actually good to do this example, because there we would really see that this lambda, this continuous parameter which we use to construct the classical solution, is not an observable, right? So what I wanted to do in this example was that I wanted to take this result for the shift in the scaling dimensions of the matter CFT, right? And in the case of the free boson, we can actually compare it with the known behavior of the scaling dimensions as a function of the radius, right? And that we can use to actually fix the relation, at least to the leading order, between lambda and the change of the radius. So that we can do. And the power, of course, here is that we can we only have to sacrifice, let's say, one state or one particular class of states to fix this relation, right? And then once this relation is fixed, this equation gives us a prediction for how the scaling dimensions behave as a function of this parameter. So that is good. But at the same time, it emphasizes the fact that the lambda itself is not observable. And actually, the particular form of the classical solution, as expressed as a function of lambda, is far from unique. I mean, it will depend on the choice of gauge which we use to construct the solution. So in our particular case, we chose the Siegel gauge to construct the solution. But if we chose another gauge, I mean, we could obtain a different function of lambda here, especially at higher orders. At leading order, I think it's kind of universal. The particular formula of the lambda dependence will, of course, depend also on the choice of local coordinates. So here at the level of just the leading order computation, the dependence on the local coordinates just dropped because everything turned out to be on shell. But starting from the order lambda squared, lambda cubed, etc., the dependence on the local coordinates will not in general drop. But as we were claiming over again during the first two lectures, the dependence on the gauge, on the local coordinates, whatever, can always be absorbed in suitable future definitions of the string field, which in this particular case boil down to the future definitions, quote-unquote, ultimate definitions of this parameter lambda. So again, the classical solution itself is not physical in the sense that it is not observable. You have to compute some observable quantities to fix this parameter lambda. I guess that's what I wanted to say.
To which order have people been able to go in the case of the closed strings?
So in this case of the closed string, I guess I have seen explicit results in papers up to order lambda squared, because at order lambda squared you will already encounter not just L2 but also L3, right? And L3, I mean, at least when in this case of marginal deformations, where the states involved in the end are just massless. I mean, you can really compute L3 without really knowing the full dependence on the local coordinates. I mean, you somehow still need to be able to parameterize the dependence on the local coordinates, but then in the end you will show that after you compute observables, that dependence drops. And I think in principle, I mean, similar procedure can be repeated for higher point vertices like L4, L5. So without just explicitly knowing what the local coordinates are. But I'm not sure I've ever seen it done anywhere. So there is this new approach initiated by Shein and company in their paper last year, based on so-called flat vertices in string field theory. So that I think if they manage to develop it, that has the potential for going to high order, because there I think the idea is to just replace the string vertices by calculating the OPs. There are some disadvantages, but in that the vertices are actually not symmetric, so they cannot be used to construct the action, but just the equation of motion. But in a sense, I mean that is all you need. But let me not go deep into that.
For the case of the open string, I guess it's just, at this point, it's completely algorithmic, even though it may be hard to any order.
Yeah. In the case of open string, you just use the Witten's cubic action, just a star product. You can go to any order. If you do not actually use the Siegel gauge, but you use what is called the curly V0 gauge or the Schnabel gauge, you can actually write an analytic solution for marginal deformation and extract everything to arbitrary order. So I guess I'll just say that lambda is not observable. So if we have again, if you are doing a marginal deformation where we already know what should happen, by the case where we are deforming the free boson compactified on a circle, right? We can just use the knowledge of how the conformal dimensions behave as a function of let's say the radius to fix the relation between lambda and the radius. But then, of course, there might be examples where we do not know what we should expect, right? Like this other example which I was giving, we can start with some special point in the Calabi-Yau moduli space, like a Gepner point, right? And we can try and turn on a marginal deformation, which would move us away from this non-Gepner point. So then, of course, we do not know we do not know where the version CFT to corresponding to a generic point in the Calabi-Yau moduli space. So we don't know what answer we should expect for these scaling dimensions, right? So then, of course, we do not have a notion of some physical parameter along this marginal manifold. So what we would probably do, we would sacrifice one of these states, right? And write down the answer for the scaling dimension delta lambda as a function of lambda, and we would actually use this as a new physical parameter in which we expand, and then we will then given that we sacrifice this one state, we would write down the different scaling dimensions of all the other states as a function of the scaling dimension of that state, right?
There's some data known about exactly that information away from the other points.
You're asking if there are some results of
Yeah.
I guess in conformal perturbation theory, maybe to some low order lambda squared, lambda cubed.
That's sufficient to carry out what you just described.
That's sufficient to fix the relation between lambda and something observable to, let's say, order lambda squared, right? But yeah. Then for instance, in the simple case of deforming the radius of the circle, the relation turns out to be that delta r over r is lambda to the leading order. Then I think there is half of lambda squared in the Siegel gauge. These coefficients will depend on the gauge of the solution, and then there will be some. I think it's going to be an infinite series in lambda. So you have to go order by order and fix this relation.
There's nothing essentially different about the free boson case compared to, say, deforming away from the Gepner point.
No. There's nothing different. The only difference is that in the Gepner point we are generally exploring something new, whereas in the free boson we already know what to expect. Okay, so let me now the final part of this lecture and of this course, and that is this yeah, sure.
How's T-duality reflected in this algorithm, these relations?
T-duality. So so T-duality is a symmetry of the vector spectrum, right? So so of course, I mean, whatever what SFT we formulate for free boson at a particular radius r, I mean, it should be the same as the SFT for, let's say, alpha prime over r, right? That is just by construction. So then you are asking.
I'm looking at that relation and I'm noticing
Yes.
lambda and lambda squared on the right, and I'm wondering how you, there's a lambda transformation that implements r goes to 1 over r, but I don't see it, and that's my.
I see. I see. So yeah, let me think about it. Because the duality not only changes the value of radius from r to 1 over r, it also exchanges the momentum and Winding modes, right? So for instance, if I were to write down a formula for the deformation of, let's say, the momentum mode, right, like that, I should not expect it to be symmetric under r going to 1 over r. Instead, I would also have to write down a formula for deformation of the corresponding Winding mode, and there should be a symmetry between these two formulae going 1 over to 1 over r. So in principle, I mean, if I expand to arbitrary order in r, that symmetry should be visible. Yeah. Yeah, so I would first have to fix the relation between lambda and r, this kind of a filter definition, and then yeah. Yeah, guys. I mean, at the level of these perturbative results, it's something which is probably not very manifest. Yeah. So so finally, let me consider solutions which are a little bit larger than marginal deformations in a certain sense, and these are small but relevant deformations. Or I would also call them short RG flows. So in contrast to marginal deformations, these are just isolated solutions. So I should not expect to find a classical solution to string field theory equations of motion for some continuous family of parameters lambda. These will be just isolated, but nevertheless they will be close to the perturbative vacuum. So they will be close to the phi plus equal to 0. So since these do not come in continuous families, as in the case of marginal deformations, I no longer have this argument that the onshore action could vanish. So here the onshore action will in general be 0, and I can actually use it to infer some interesting observables, right? Because the onshore action, since it is gauge invariant, it should be connected to something observable. So as I was already commenting on, in the case of gauge string field theory, it is still a bit controversial what the value of the onshore action should correspond to. On the other hand, in open string field theory, it is conjectured, and that conjecture has been widely tested and proved, that the value of the onshore action should correspond to the change in the disk partition function of the version CFT. Df is the partition function. So this is what people call the sense conjecture. You can call it a conjecture or theorem depending on what your level of rigor is. So to what extent you believe this proves. So in particular, in the remaining time, I will just try and test the leading order this sense conjecture in the case of the short RG flows. So at the level of the rigid CFD, we can also say that the disk partition function is something which is proportional to what can be CFD or the G function. So the change in the disk partition function should precisely measure the change in the G function from the boundary state which we start with, which we use to formulate our string field theory, to the boundary state which corresponds to the classical solution described by this short RG flow. So then of course there are known results in conformal perturbation theory, mainly due to Affleck and Ludwig, telling us what this change in the disk partition function or G function should be. So whatever we find out from a string field theory calculation of the on-shell action corresponding to this classical solution should precisely match with these conformal perturbation theory compositions. So let me try and do exactly that.
Unification générale. On vous informe que le CES Athlète procédera à un essai de sirène aujourd'hui à 12h15. Ainsi, un modulé spécifique sera émis pendant 1 minute et 48 secondes.
Can I just continue or?
Well, he'll probably say it again.
Yeah. Okay, let's just try my chances. So,
Okay.
So similar to what was happening in the case of marginal deformations, where we were triggering the solution by a quote unquote master state, by a state which was inside the kernel of L0 plus. In this case, we will be triggering the relevant deformation by slightly tachyonic states. So for the sake of definiteness, let me now focus on the case of open string field theory. So the solution which I will be interested will be triggered by states of the following form. So here, since I'm in the open string, I'm just focusing on the chiral half of the CFD. So if I were to write down something which would have corresponded to a marginal deformation, I would have chosen a state which would go like C1, and then a state in the measure CFD which would have dimension 1, right? But since now I want to be slightly tachyonic, I'm picking a state which has dimension 1 minus y, where y is something small and positive. So that's the idea. I'll write down a solution which at leading order, where by leading order, I mean leading order in this small parameter y, which starts exactly like that. And then, by feeding this into the classical equation of motion, I'll try and compute a higher order corrections to that solution. So before I do that, just give me a couple of examples of particular short RG flows which take place. So one example would be reasonable typical RG flows in models, right? So as you may know, the Milling models, these when I restrict to the unitary series of Milling models, they have center charge C, which I can parameterize to using an integer m as follows. Right. So you can notice that as m goes to infinity, that's when the charge approaches 1 from below. And then there is a particular class of states which have Katz labels 1, 3, and the dimension of these states can precisely be written as 1 minus something small, where something small roughly goes like 1 over n. So for each m, you can choose to deform the minimum model by this operator that will trigger an RG4, which is short because that dimension is close to that state is close to being marginal, and the answer is that will actually if you trigger this RG4 in the bulk, you will fall to a minimum model with m minus 1. There are also analogs of these homological RG4s for boundaries. So in that case, there will be, I mean, you can always choose a suitable Cardi brane for a fixed minimum model, where in the boundary spectrum of that Cardi brane, you will also have this operator 1, 3 with this almost marginal dimension, and that will trigger boundary RG4, which will not change the label of the minimum model, but it will change the Katz label or the Cardi label of the boundary state for the fixed minimum model. So that's just an example of these short RG4s. So now let me very quickly outline the construction of the corresponding solutions in the SFT. So for that, I will be following some recent references. So let me just give you the references. There are the 2 papers by Martin Schnabel and Jaroslav Frankfurt. 05216 2308 16142. And then there is also a paper by Ben Mazel, Charles Wang, and Xiyin last year. So the strategy which I will use to find a solution corresponding to the short RG4 will be very similar to what we did for the element of the deformed cohomology in the case of marginal deformation. So we will try and solve for successive approximations to the solution. Well, that is to say that we will try and construct the string fields by bracket n, which will be supposed to be the exact classical solution plus possible corrections of order y to the n plus 1. So taking this ansatz and substituting into the classical equations of motion, I will again get some successive conditions in n to satisfy. So first, for n equal 1, I will just get that equation. For n equal 2, I will also get a contribution from the interaction. By this interacting term, I will be already feeding the inside these interaction terms. I will already be feeding approximations of whole order, which I found by some previous conditions, etc., etc. So again, let me start with the first equation, and then we can see that it's already solved by the ansatz, which is supposed to trigger the short RG4. So in particular, let me repeat the ansatz. So the ansatz for phi 1 is in general some coefficient which will be of order 1. Let me call it G1. Then y C1 B 1 minus 1. So I'm putting this y because of course we want the solution to be close to Birchbark vacuum, and in particular if this parameter y is taken to be 0, we just want to recover the Birchbark vacuum, right? So so then of course checking that this first condition is satisfied is equivalent to checking that if I act Q on that equation, I will get something which is order at least y squared. And indeed, that is what is happening. If I act with Q here, again, this is a state in the CU gauge. It's killed by B naught. So as such, we know that acting with Q on that state is as good as acting with just C naught L naught. So computing L naught on that state here, I see that I get -1 from the C ghost, and then I just get the dimension of this V 1 minus y, which is 1 minus y. C naught C1. So these ones, they just cancel, and all I remain with is this power of y, which gets combined with this power of y to get something of the order y squared, which is enough to satisfy this first condition. So then you may ask, we were allowed to put a completely arbitrary value of G1 here, of this coupling, right? So is this what we should expect, or should we expect this coupling to be fixed? So this coupling, you of course see that it's something which should, roughly speaking, correspond to the coupling which we add to the state when we deform the original worldsheet action by perturbing with this almost marginal but slightly relevant deformation. And of course, we know that this coupling needs to be fixed to a particular value. In the case of conformal perturbation theory, we would use the worldsheet beta function to fix the value of this coupling. And indeed, we will see that this coupling will be fixed, but it will actually be fixed not by this equation at leading order, but by the equation arising at subleading order. So then, that being said, let's worry about the equation at the subleading order. So again, I will do something which should look already very familiar to you. I will take this solution at the subleading order, and before I solve for it, I will decompose it into two parts, into part which I call little phi 2 and part which I call capital R2. And this part little phi 2, I will define it to be projection of the full string field inside the kernel of L naught, plus possible corrections which are of order y. So this is my definition of this projector, which defines the state capital, lowercase phi. And on the other hand, this is what I will call P of y by 2. On the other hand, this is whatever remains. So this is defined using the corresponding projector 1 minus py. Okay. So then again, I can do the familiar thing. I can use this projector to split this equation at second order into two equations, one for the lowercase phi and the other for the capital R. And again, inside this product, I can replace the capital phi with lowercase phi, because at the leading order we knew that the whole string field was already given by the ansatz, which was inside this kernel of L0 plus corrections of order y. So that is the equation for lowercase phi. And then there will be now this equation for the capital R. It will be Py bar and to same. So now, as I was exercising, let's see how we get how we can now get a restriction on the value of this coupling G1, which we were including in this solution arising first order. So I would just say that the second equation for capital R that can be again solved by the usual means. You can just take this Q, and since this state is projected to be far from the kernel of L0, we can just insert this Q in Siegel gauge by acting with B0 over L0. So that I will not even discuss anymore. And let me just focus on this other equation. Yes. So that is, we want to solve for phi2. So we do that by writing what phi2 should look like. So phi2 should be a state in this almost kernel of L0. So kernel of L0 plus corrections of order 1. And for the sake of simplicity, let me assume that the CFT which I'm interested in is chosen such that the other state in this kernel of L0 is the state which is triggering the relevant deformation. So in general, of course, I mean that isn't going to be true. I mean there can be relevant deformations which go in multiple directions, and then I would be solving complicated equations for the couplings, etc. But just for the sake of illustration and for the sake of simplicity, let me assume that the other state in which is close to marginality in this particular background is precisely the state of V1 minus Y, which I was using to trigger the relevant deformation. So that already guarantees me that I can write the solution phi2 in this form. Again, it will be G1 Y. But now, since this is to be an approximation which is one order better, I can also include some coupling G2 Y squared C1 V1 minus Y acting on a vacuum. So then I can compute what Q on this phi2 is, right? Because that is precisely the first term of this equation of motion. So what I will get is minus Y G1Y plus G2Y squared C0 C1 V1 minus Y. Again, I'm using the same logic. I'm just acting with C0 L0. L0 gives me this minus Y, and this is the C0, right? So you can see that if I want to solve this equation of motion to the order of Y squared, I can forget about this term with the coupling G2, right? That will not be fixed. And similar with G1, the G2 will then be fixed at order Y cubed. Okay? But now, in order to solve for this G1, I know that if I want to solve this equation, I need to compare this calculation of Q on phi2 with minus P on M2. And here I can substitute for this phi1, that is the ansatz at order y to the 1. So here I get minus G1 squared Y squared P0 M2 CV1 CV1, where here, okay, in principle, I should have written 1 minus Y, 1 minus Y, but since I have order Y squared in front, and I'm solving this equation just with the accuracy of Y squared, I can just replace this state with its analog at a dimension which is exactly equal to 1. So then I'm in a very analogous situation as in the case of this different homology calculation. I can notice that that here I am calculating the two-string product on the states which are exactly on shell. So one way to proceed would be to take an overlap of that equation, both left and right hand side, with a state which is exactly C1, right? The other an equivalent approach would be just to compute this string product M2. Again, that computation will be independent of the choice of local coordinates because I'm inserting on-shell states. And what I would have obtained is just C0, C1, CVV, B, V1 on the vacuum. Now this is the OPE coefficient of V with itself. So this is the coefficient arising. So if I do the OPE of V of Z with itself, so at leading order, I will get 1 over Z, 1 minus phi, right? Then I will get CVDV V Z to the 1 minus phi. So this is the coefficient in the OPE of V itself arising at this kind of almost order 1. So then I can just compare the two sides of the equation of motion. So this is the right-hand side, and then the left-hand side is whatever I got from computing Q and phi 2. And you see that in order for the equation of motion to be satisfied, I need to have that G1 is equal to minus G1 squared CVV. So that fixes the value of the scattering G1 be 1 over CV. So then, just looking at this result, you can ask, so what would happen if this coupling is just not there, if CVV is 0, right? So then that would mean that I'm unable to balance this equation, right? So that should be thought of as analogous to this obstruction which we are observing at subleading order for the management of information. So in this case, it would be saying that the short Archie flow does not exist, and that whatever Archie flow is triggered by this operator, it will actually not be short. For instance, in those cases of the zonometric of Archie flows, which I was giving you as examples, this structure constant when V is taken to be this primary with 1, 3 cuts label, I mean that is non-zero. So in that case, the short Archie flow actually exists. So then we can summarize by writing down the solution, which is exact to the order on the squared. Y over CVV plus G2y squared. So this G2 is unknown, as I was saying. In order to fix the G2, one would have to go to order y to the cubed. Also, for the leave this part R2, but that R2 is straightforward to solve for, as I was. So the final thing which I want to say is again that what we have now is a solution, but that solution is not really observable. So let me finish the thing which I wanted to do, and that is to calculate the on-shell action, at least the leading contribution or the leading order of accuracy of the on-shell action on this solution, and compare it with the known result from the conformal perturbation theory. So so the on-shell action first we have the kinetic term, which is just phi q phi. So if we want to compute the onshore action to the leading order in accuracy, let me just actually substitute one. So that is the lowest order of accuracy to which we know the solution, right? And let me try and read off what the corresponding order of accuracy of S is, right? So we know that phi starts with the power of y. So there is there are two powers of y coming from each of the phi one individually. But then we know that when we act with q on phi, right? Since phi is almost in the kernel well not, it will drop us another power of y. So so this term will turn out to be a power of y to the cubed, right? And what we are writing is in fact a contribution to the onshore action, which is exact to the order of y to the cubed. So that at the same time tells us that in order to get the correct answer, we also need to consider the cubic coupling. Right, so that will also be of order y to the cubed. But then since we are evaluating this action on the classical solution, we can actually use the equations of motion, so that we don't have to compute separately these two terms, but we can actually remember that m2 on phi 1 is the same as q on phi 2 with a minus by the equation of motion. So we get 1/2 minus 1 over 3. So that means that in total we get 1/6 omega phi 1 q phi 1. And then we can substitute the solution to the leading order of accuracy. So first for this phi 1, we can substitute y over CVD, C1 V1 on the vacuum. And then for this q on phi 1, we can substitute. So this q will drop us just an additional power of y with a minus y squared over CVD. C1 V1. But then if we just compute the VPZ product of these states, what we end up with is minus 1/6 y cubed over CVD squared. And now, okay, I will write something which may sound a little bit awkward, but this is the 1-point function of the identity operator on the other half way. So if this was the 1-point function of the bulk identity on the sphere, that is usually normalized to unity, right? But on the upper half plane, this is something precisely which can give us different values for different BCFTs, and it is normalized to be the disk partition function or the G function for the given BCFT. So then, given that this is the leading contribution to the onshore action, we can just use the sense conjecture to see what the corresponding change in the disk partition function is. The change in the disk partition function corresponding to going from the old BCFT corresponding to the UV BCFT to the IR BCFT, which is the fixed point of the short RGFO, right? So then the precise form of the sense conjecture is the delta G over G should be equal to 2 pi squared times the onshore value of the action. So then substituting that result, you will get minus pi squared over 3 y cubed over CVD squared. Plus corrections which are higher order in experiment. So that's the final result. So before I finish, let me just make a couple of remarks. So the first thing we can do what I was promising to do, and that is to compare this with the known conformal perturbation theory result, which was due to Ian Affleck and Andreas Ludwig, and yeah, we get a precise match. Yeah. So this is the CPP answer obtained by those guys. But what we can mainly notice is that those guys actually obtain it as a result of a very complicated calculation, which in this conformal perturbation theory setup was actually arising at two loops, right? So it involved a very subtle, very complicated procedure of regularizing collisions of integrated operators along the boundary of the disk, and then just focusing on the universal part. And yeah, I mean, you can read it in that paper from the beginning of the 90s, and it is really complicated. Whereas here, I mean, we obtain the same answer from string field theory just by multiplying numbers, basically, with no need for regularization, etc. Of course, then when we go to higher order in Y, we will the calculation, even at the string field theory level, will get more complicated. But still, it will be straightforward and well defined in the sense that at each and every step, if we follow these rules of string field theory, we should be able to get an unambiguous answer for the change in the G function without any necessity of introducing any ad hoc regularizing parameters. Yeah. So yeah, I think that's a good place to stop.
Thank you. Questions for Jakub?
Clarify the difference between this relevant deformation and the previous continuous deformation, because here Y is very similar to lambda before. Can you just emphasize the difference?
So you're asking for the difference between the relevant and the marginal cases?
Yes.
Yeah. So yeah, in the case of marginal deformation, we expect the solution we expect there to be a consistent CFT to be for continuous values of parameter lambda, right? Here, on the other hand, the relevant deformation is expected to be a fixed classical solution corresponding to the IR CFT, to the CFT in the IR or the RG flow. But still, in order to be able to say, in order to be able to develop this perturbative argument, right? We need a parameter in which we want to expand, right? So this parameter Y, that should not be thought of as a parameter of the solution, should be thought of rather as the parameter of the UV CFT which we start with, right? So I'm assuming that the UV CFT which I'm starting with comes in a family, right? Which can be parameterized by this parameter Y. And in that family, I'm able to identify a particular class of operators, or in this case, a particular operator, which is parametrically close to marginality in that parameter Y, right? So going back to that example of these homological flows, right? So that family is precisely the family of all unitary minimum models, right? And this parameter Y is to be identified with this 1/m, where m was the parameter, right? So in that family, I'm picking a particular CFT at a particular value of Y, or that is to say at a particular value of 1/m. And at this particular value, I'm constructing this perturbative solution corresponding to the relevant deformation, which actually in that case turns out to take me to a different value of m, right? But yeah. That is just a particular feature of that example with the logic of RG flows. Another example which we are currently exploring with multiple collaborators, including Daniel and Thibault, arises in the case of Narayan CFTs, right? So in the case of Narayan CFTs, you have the whole you have a whole marginal manifold where you can parameterize your states by the parameters of the by the Narayan moduli, basically, right? So you can actually discover that there are some specific regions, some points in the Narayan moduli space where, as a function of some subclass of parameters of subclass of these Narayan moduli, you can construct operators which are parametrically close to marginality, right? So so there again you can hope to construct these short Archie flows. That actually applies to the case with a boundary. In the bulk, there are also operators in the Narayan moduli space which you can tune to be close to marginality. There somehow you fail to satisfy this condition on CVV to be non-zero, and actually that do not seem to be any examples of short Archie flows in the bulk of the Narayan lattice. But yeah, as soon as you start including boundary states, then there seem to be examples of short Archie flows between boundary states at a fixed value of the Narayan modules.
More questions? Always ask more questions at lunch, but yeah, let's thank Jakub again for the fantastic course.